Okay, so we have now Adam Taras, from Leiden Observatory, talking about Nulling interferometry with VLTI.
Sorry. What? Yep. Cool. All right. I'm Adam Taras. I'm a new PhD student at Leiden Observatory, but this is some work I've done previously at the University of Sydney. And I'm going to hopefully convince you that fringes are friends by talking about nulling interferometry at the VLTI with the Asgard instrument suite. And we're going to try and turn the VLTI into this Asgard paradise. So, a bit of background on nulling interferometry. You can bring the light from two distinct telescopes together, and if you apply a pi phase shift to one of them and then combine the light, you can actually null out starlight that's on axis. And so if you look at the contribution from different positions in the field through this sieve, you can put the star in the center and get no light from the star, and you can get light through from off-axis sources. And then as the sky rotates, you're actually able to figure out where these objects are and what they have. And also, I'm showing it here for 3 different baselines. You can see longer baselines allow us to reach in much closer to the star. An updated, iterated version of the simple nuller that I showed on the previous slide is called kernel nulling, where you use a 2-stage system, shown in the top right here, and this makes it more robust to piston errors. I'm going to not talk through the details too much and just show you an example. If you had an example observation here with an off-axis companion and some phase errors, you might get a distribution that looks like this in the classical case. If you do it with the kernel nuller, you get some more outputs, but because you have clever post-processing and you do a subtraction, you actually get these distributions on the right, and you can see that they're much narrower, even though the phase errors that were injected are the same for both cases. So this is the critical ingredient that we're going to be using for nulling interferometry. So now to the Asgard instrument suite. This is phase 1, which is currently at the telescope. We have an alignment and calibration unit. On the lower level, we have a fringe tracker in the K-band that's built with bulk optics for high sensitivity. And on the upper level, we have a second-stage adaptive optics system using a Zernike phase mask. And these two actually share the same detector. And then later in the year, we've got 2 science instruments. NOT, which is going to be the focus of this talk, and also a stellar interferometer. And NOT is going to be the first long baseline nulling interferometer in the southern hemisphere and sensitive down to giant exoplanets at 5 milliarc seconds. So just to give you a brief overview of the timeline here, we have some of the instrument already commissioned in September last year on some of the smaller telescopes. We'll be commissioning on the larger telescopes in April. And then, as I mentioned, later in this year, we have the simple nulling mode coming with a low spectral resolution. And the stellar interferometer is also going to have the low spectral resolution commissioned. And this is all in ESO's 117 period. And then into next year, we're going to have this kernel nulling with disk and planet mode and some higher spectral resolution. So why do we want to do this? One of the key science cases for the Asgard instrument suite is to directly image hot Jupiters. And in particular, the L-band is well placed to image these objects. So here I'm showing the contrast as a function of wavelength for a few different objects with the colored lines. And you can see as we go to longer wavelengths, the contrasts become more favorable, but the thermal background also increases. However, at short wavelengths, you've got higher effects from phase errors. And so the L-band is quite nicely placed here to do this. However, to make a convincing detection, you need a fringe tracker and an adaptive optics system, which you can see in the difference in the 2 dashed lines there. And you need a fringe tracking down to about 100 nanometers RMS to do this well. This will let us access a new area of parameter space. We've seen a lot of parameter space plots where everything is well off into the at least 100 milliarc second range. We're really probing down to the few milliarc seconds with this instrument suite. And we particularly will be able to image a few planets, and by measuring a dynamic mass and the luminosity in just a few spectral channels, we can constrain different planet formation models, both from gravitational instability and core accretion. Another important science case is understanding exozodiacal dust. Exozodiacal dust, I'm showing here a sort of solar system-like schematic where you have cold dust on the outside and then it gets warmer as you come in. And in our solar system, the exozodiacal dust integrated is brighter than all of the planets combined, at least in the optical and near infrared. And so this has also been detected in a wide variety of other systems in previous surveys. And in particular, this hot exozodiacal dust close to the star is poorly understood and needs to be better constrained. And the reason for this is that it has the potential to contaminate future high-contrast imaging instruments. So here's an example of an unsuccessful recovery of an off-axis companion because of this exozodiacal dust. And so in particular, the Nulling interferometer in Asgard will be 50 times more sensitive than previous surveys and will help vet targets for these sorts of missions. So now I'm going to go on to the status of the instrument. So first I'm going to talk about the fringe tracker. This is some data that maybe people aren't the most used to seeing. So I'm going to show first 2 simulation videos showing what the fringe tracker looks like at 500 nanometers RMS on the left and 100 nanometers on the right. And that looks like this. So it's actually, it's a 2-dimensional fringe pattern, and we're trying to keep the central peak bright. And you can see that's only possible when you're down at this 100 nanometers RMS. So that was in simulation, and there's something a bit funky going on with the video there. And then down the bottom here is what it was like on sky. And so you can see that even though the adaptive optics system has some tip-tilt residuals, we're keeping this bright central spot in the middle. And it certainly looks more like the 100 nanometer RMS case. And indeed, when we look at the numbers, it's about 80 nanometers RMS. And just to give you a sense of scale, we're doing this over a distance for 2 apertures that are separated by 120 meters. So the implications for the Nulling interferometry can be drawn from this previous prediction in a paper. If we're sitting at this level for realistic amplitude fluctuations, we expect a contrast uncertainty of about 10 to the minus 5 if you're limited by fringe tracking residuals. And so this is quite promising. This also obviously depends on background since you're at such long wavelengths. So for faint objects, your contrast is limited by background, shown in blue there. The other part of the instrument that was commissioned was Boulder. So this is needed to robustly inject light into the photonic chips that are used for Nulling interferometry. And we were able to only close the loop intermittently, but here's an example of it it working and reducing the tip-tilt residual with the open loop in blue and the closed loop in red. And there's actually further commissioning going on this mode, starting, I think, tonight. So certainly something that's ongoing. Watch this space. And as part of the risk mitigation strategy, in addition to the Zernike wavefront sensor mode, we're also going to be adding an image plane operating mode that just monitors tip-tilt. So the other part of the instrument is the Nulling interferometer itself. The photonic chip has been characterized. This is what it looks like. It's really quite small, and this is one of the advantages of these technologies. And they've also managed to do broadband nulls in the warm. And so here I'm showing an example for the planet mode, where you have the 2 bright channels and the 2 faint channels, and then similarly for the disk mode. And again, ongoing work, they're actually doing this month, is some integration in the cryostat to get things down to the cold temperatures that are needed, and to also do this with some spectral dispersion. So to summarize, Asgard is a visitor instrument at the VLTI. It's part of the next generation of instruments at the VLTI, and it's going to provide Nulling interferometry. Our science involves planet formation tests at the few milliarc-second level and understanding exozodiacal dust. But I also want to advertise that we are open to collaboration, and you're welcome to submit ESO proposals with our consortium, even though this is a visitor instrument. And phase 1 has been commissioned, and phase 2 is ongoing / later this year. Thank you for listening. Happy to take questions.
I wonder if you could tell us a little more about the photonic chip for NOT. I was curious why it has to be cold and whether you have active phase shifters on the chip itself.
Yep, that's a good question. So the chip itself, I mean, the imaging setup needs to be cold so that you're able to do the L-band measurements. Otherwise, because you're imaging the face of the chip at the output. So if the chip was warm, you'd be seeing more thermal background. The other question about phase shifters, not in this generation, I believe. There are extra delay lines upstream, and there's also some innovation with carbon dioxide compensation, but at least not at the moment for the phase shifters. Yeah.
You showed some predictions for the null. What is your end-to-end throughput? Do you have any estimates?
Sorry, the throughput.
End-to-end throughput through the nuller. Yeah.
Okay, so I mean, keeping in mind that VLTI itself is low throughput compared to single telescope instruments. There's actually a lot of infrastructure that goes into obviously the delay lines and such. I think we get a throughput of about 1% all the way to the chip, but that's still to be validated once we integrate on site.
When integrating on VLTI, are there any particular things you're most worried about, such as like maybe the vibration environment at VLTI or things like that?
Yep. So certainly we commissioned on the smaller telescopes, the ATs, and we got to the level that gravity's at relatively quickly. We're also running at a factor 2 times faster than gravity, so we're actually able to compensate for some of the effects a bit better. But once we commission on the UTs, we'll have a better understanding. There's also some upgrades in general to the VLTI infrastructure to mitigate these vibrations. We're fairly confident that it won't be a limiting factor.